Welcome. In this lecture, we'll examine another set of multi-table operations. While these operations have practical application, we want to note that these operations are tied more closely to the theory of relational database. Relational database contains a set of relations, which are actually sets. The choice that most commercial products make for representation of these relations is a table. So the operations we'll be providing here are set-oriented or set-level operations, but they will be implemented in such a way that they're applied to tables. So the operations we'll be discussing will be union, intersection, and set difference. So let's get started. The model upon which relational databases are based formally defines a table as a relation. A table is the choice of a representation for the relation that we see in most commercial products. Because a relation is a set, it should not be surprising that the relational model includes a collection of set operators that can be applied to these relations, hence to these tables. The implementation of these operators in a relational database is the subject of this current video. We'll discuss these operators and provide some context where they might prove quite useful in practice. The operations include union, intersection, and difference. Implementation of these operations in commercial systems has evolved over time. Union has been directly implemented by commercial products essentially from the beginning. But initially, the set difference and intersection were not implemented by all commercial products. So the lack of a direct implementation of difference and intersection was not a deal breaker, however. The effect of these operations can also be achieved through subqueries, so we'll demonstrate this later in the video. All set operations combine the results of separate query blocks, what we think of as select statements, by merging these results in a single result. To enable this merging, intermediate results produced by individual query blocks must be union compatible. What union compatible means is that all select lists in the statements or the query blocks that are being combined must first have the same number of expressions. Second, the corresponding columns from these select lists must be of the same data type or can be converted explicitly or implicitly. Thus, they must be of compatible data types. Before examining the SQL, where these operators have been implemented in relational database, let's consider the behavior of these set operations. We'll be using two tables, Table 1 and Table 2, and the rows in each table are shown here. Notice that there are some rows that are common to Table 1 and Table 2, and also Table 1 has some rows which are not present in Table 2 and vice versa. So the union of two sets will provide the combination of the members of the two sets and will not preserve the duplicates. That is, if any value appears in set 1 and also in set 2, it will appear in the union only once. The same applies to this implementation of union with respect to tables. Observe that there are rows that are common to Table 1 and Table 2. The union of the tables shows each of these rows only one time. This means that union effectively removes duplicates. This is the behavior we are familiar with from set theory, as sets do not have duplicate members. Also note that the manner in which result tables are combined is quite different from the way we combine tables with a join operation. As we discussed join, we considered a join to be the concatenation of rows from two tables. This was obtained by appending data from one row to data from the matching row from the other table. The set operator might be thought of as stacking the rows on top of one another. Thus, the degree of the resulting relation or table for a join will be the sum of the degrees of the participating tables, while the degree of the relation or table that results from applying a set operation will be the same as that of the participating relations. This aligns with the reason for union compatibility. Intersection seeks to find those members that are present in both sets. In the case of a relational database, what we're saying is we have the output of two query blocks defining our sets, and we're looking for those tuples or rows that are present in both sets. So the intersection will capture that commonality, and again, duplicates will not appear in the result. So in our example here, one table or query block produces the set of rows that we see with the label table 1, and the other query block produces the set of rows with the label table 2. Notice that D, E, and F appear in both sets. Those are the only rows that will be present in the intersection. An observation we can make at this point regarding union and intersection is that if I say table 1 union table 2, or I reverse the order of the operands, and I have table 2 union table 1, I get the same result. Likewise, with intersection, it does not matter whether I say table 1 intersect table 2 or table 2 intersect table 1. As we examine the set difference operator, we'll see that this is no longer true. With the difference operator, we seek to find the members in one set that are not present in another set. In our example, we are again using tables 1 and 2, but changing the order of these tables with respect to the difference operator produces a different result. Table 1 minus table 2 produces those rows that appear only in table 1 and are not present in table 2. Table 2 minus table 1 produces those rows present only in table 2, but not present in table 1. The ANSI standard defines this operator, the set difference operator, as the keyword except. And you'll find that except is supported by IBM's DB2 Microsoft SQL Server, among other systems. Oracle Database supports this operator using the keyword minus. Oracle supported this set difference operation before other systems adopted it. They chose to use the word minus, and to this day continue to support the keyword minus rather than except. Before we consider any examples in SQL involving the set operators, let's consider why this operation, or these types of operations, are of practical use. Consider, for example, in our conceptual design, as we developed our data model, we discovered an employee as an entity type. Furthermore, we recognized that there were two distinct versions of employee. We could have faculty, whose role in the institution would be to teach classes and advise students. But we could also have staff, whose general role within the institution is to perform various administrative functions. The behavior alone is not what causes us to focus on a distinction between the two types of employees, but rather the importance comes from the idea that we have different descriptions. There may be many different attributes associated with faculty that don't apply to staff, and likewise various attributes that apply to staff that don't apply to faculty. So the combination of the functional or behavioral difference as well as structural difference says perhaps instead of implementing a general employee table, it makes sense to implement tables from the subtype so that we would have a faculty table and a staff table. And that's exactly what we've done in our database. Now, the consequence is, in situations where questions are presented to the database that require looking at all of the employees, regardless of which category, faculty or staff, what we need to do is to access two tables. If we want to present a general answer that relates to employee, we need to merge data extracted from these two tables. That's the motivator with these set operations. So let's examine the union operator as implemented in SQL. As suggested earlier, union is going to combine the results of two query blocks and merge these results into a single result table. The union keyword is recognized in SQL. It represents the union operation. We would have one query block union another query block. Here we're selecting the names of faculty and merging that with the names that we select from the staff table. This would give us a list of all of our employees. Here we have two select statements that are combined by placing the union keyword between them. Each select statement is a query block. It determines the set to be processed. Because a mathematical set must contain distinct values, the result of the union operation, which again is a set, will not contain duplicate values. The result may appear to be sorted, even though order by is not specified. This is because many systems typically perform an internal sort to identify duplicate values for purposes of their removal. Let's examine this operation and the result that it produces. The tables for the types of employees have different column names. Faculty has a column called FName, while staff has a column called EName. Note that the corresponding column names in the query blocks do not need to be identical. However, only one name can appear as the column heading for the displayed result. Note that the name of the column in the output of this union is FName. In general, the column name that appears in the first query block will determine the column heading of the output. The query blocks in our previous example had columns with different names. There may even be times when using either of the names would not be the best way to describe the content of a column. So we're going to look at a way to rename the column. We already know the concept of renaming a column in the query output. But when we do it with a union operation, there are multiple query blocks. All we need to do is to apply the new name or the rename operation to the first query block. This is what controls the output for the overall result of the union operation. In this example, that column is going to be supplied with the name of employee name. Another important observation can be made regarding this statement and the union operation. In our database, no two faculty have the same name, no two staff have the same name, and no faculty and staff share the same name. Thus, there were no duplicate name values encountered in the processing of this statement. This means we cannot confirm the duplicate removal behavior of the union operator from running our first couple of queries. So let's look at a query where duplicate values will be encountered. In this statement, we wish to identify all departments that have employees. Note that a department that employs staff only and has no faculty will be reflected in the output. Likewise, a department that employs faculty only and has no staff will also be reflected in the output. And finally, a department that employs both types of employees will be reflected or reported in the output. So regardless of the number and types of employees, a department will appear only once in the output. If we extract and run each query block as a standalone statement, we'll confirm that duplicates were present in the tables and that the duplicate removal behavior of the union really did occur. Set theory defines the union of two sets as the set of all values taken from both sets. Because a mathematical set must contain distinct values, the result of the union operation, which of course is a set, will not contain duplicates. Here's an example. Suppose we have set A that consists of the even integers 2, 4, 6, 8, and set B consisting of 1, 4, 5, and 6. The union of these two sets will be 1, 2, 4, 5, 6, and 8. Although 4 and 6 are members of both sets, 4 and 6 will each appear only once in the resulting union. So the same principle applies to the formation of a result table, which is the union of two or more intermediate tables or query blocks generated by independent select statements. Note that duplicate rows are not displayed or not present in the result, even though you have not explicitly specified the distinct keyword. However, it might be desirable to preserve the duplicates in the result, and this is possible. We can still merge data from query blocks, yet retain duplicates. This is demonstrated in our next query. If we use an operator called union all rather than the traditional union operator, this will preserve any duplicates that might appear in the processing of the two query blocks. If the optimizer of the system uses a sort to remove duplicates, and the duplicates are preserved by using union all, the result is not incidentally sorted. Remember, we said sorting could potentially be a side effect of union if the optimizer uses a sort operation for duplicate removal. But with union all, we will not see the result sorted as a result of this operation. However, if the result must be presented with the rows in some order, an order by clause can be used with this statement. In the current example, we might add order by department, the name of the column appearing in the result set. Or we could say order by one, the position occupied by the department column in the left to right display of columns in the result set. In either case, the order by would be placed at the end of the entire statement. The query blocks that are combined with union are not limited to retrieving only a single column. The select statements need not retrieve all rows from a table, but can include predicates. Our next query will demonstrate both of these concepts. In the first query block, we're selecting the name, the department, and the title. 3 columns from the staff table, and only for those rows where the employee works in the theology department. The second query block also selects 3 columns, this time from the faculty table, and again, only for those employees who work in the theology department. We then combine these two sets. So note that union compatibility applies here. Each query block must have the same number of columns. We've satisfied that requirement. Each query block has 3 columns. Additionally, union compatibility says that the corresponding columns must be of a compatible data type. E-name and F-name are both character strings. Department and F-department, both character strings. E-title and address, both character strings. We've satisfied the second requirement of union compatibility. However, observe that the third column in each query block contains character data, but the columns represent values with very different meanings, job titles and addresses. The system only requires that the 2 columns be of a compatible data type because they'll be stored together in the same column of the result table. It doesn't look at the semantics or the meaning of what's represented in these columns. Also, we noted earlier that the final result of a union can be explicitly ordered. That is, we can include an order by clause. Here, we've used this to reference the column in the result set by its relative column number or its relative position. Order by 1 in a descending sequence. This will cause the result to be ordered by the value of the employee names. Additionally, we should note that the order by clause can appear only once. It must be the last clause of the entire statement, positioned here after the query blocks have been merged using the union operator. The examples that we've seen thus far have involved merging the output of 2 query blocks. It's possible to merge more than 2 query blocks by using an additional union operator, as demonstrated in this example. The first query block produces the average lab fee for lower courses or introductory courses, those courses with a course number that ends in 1 or 2. We combine that with the average lab fee for courses where the course number ends in 3 or 4, intermediate level courses. And finally, we produce the average lab fee for courses whose course numbers end in 5 and 6, upper level or advanced courses. Because we're selecting a derived value, the constant lower, intermediate, and upper, even if any of the averages for the different groups happen to be the same, each row produced by the query block will clearly be different from any of the other rows. For that purpose, we've chosen to use union all to combine the results. An additional comment before we leave the union operator is that query blocks can be complex. A query block is not limited to retrieving data from a single table. All of the examples have queried just one table, but it's possible that the query blocks could involve more advanced operations, such as a join. Consider the following example. Each query block relates to one type of employee. Information about that employee is combined with information about that employee's department. Like the union operation, intersect combines multiple query blocks into a single result table. The result of intersect consists of those rows that are common to the two intermediate tables. We had mentioned earlier that intersect is superfluous in SQL because the operation can be achieved using a subquery, and we'll demonstrate that in just a moment. And the other set operation, set difference, is accomplished by using either the word minus in the case of Oracle database or the word except for many other ANSI standard database systems, such as IBM's DB2 and Microsoft's SQL Server. Recall in our discussion of set difference that it is important to recognize which query block precedes the difference operator and which follows, because we can get a different result. The operation is not commutative. So only rows present in the staff table and not present in the course table will appear in the result. And again, if the two statements were reversed, the result would be quite different. Set difference is also superfluous in SQL because we can produce the result using subqueries, and we'll show that in just a moment. But a final comment regarding both intersection and difference is that with these operators, the two query blocks must again satisfy the union compatibility requirements. Using correlated subqueries with the exist operator, we're able to produce alternatives to intersection and difference. The first example produces the intersection of the two tables, and the second example, using not exist, produces the difference of the two tables. Why it's beneficial to understand this is historically the set difference was not implemented in all commercial database systems. So for that reason, queries could have been written using exist or not exist to accomplish the idea of intersection and set difference. Furthermore, if we're dealing with set difference, there are two different operators, minus in the case of Oracle database and except in the case of many other databases. If we'd like to write the code so that it works on different systems, but only have one version of the code that we need to maintain, using the correlated subquery would not exist might be the way to go. And finally, with that understanding, we could actually write an outer join without using an outer join operator. Recall that the outer join consists of the inner join plus the additional non-matching rows from another table. Our first query block is going to produce the matching rows, the inner join, and the union all will serve to combine that result with the second subquery using not exist, which is going to produce the non-matching rows. Well, this video has provided you with a fairly comprehensive examination of the set operations as implemented in SQL. We talked about a little background to review the concept of the set operations of union, intersection, and set difference. Then we examined how they were implemented in SQL. Union actually has two implementations, kind of the traditional union that you're familiar with from set theory, plus union all, which preserves duplicates. We then talked about intersection, which is implemented in SQL with the keyword intersect. And finally, we talked about set difference. And set difference is implemented in the ANSI SQL standard with the keyword except, but in Oracle, they adopted the keyword minus. We showed then an alternative to using the keywords for intersection and for set difference by writing correlated subqueries. I hope you found this useful and informative.